implementation of mass transfer in the Interfoam network, which is basically a POF solver available in OpenFOAM. So I'll be basically explaining all the basic procedural steps that we go through for modifying an existing solver, so this will be able to capture the kind of phenomenology that you are trying to implement into your modified solver. So to give you a background of this work, so initially you might have seen those animations from actual video from the experiments wherein we were having mass transfer from the organic droplet which was ascending and descending in the water column. So this work is something related to that. So in order to capture the mass transfer from the dispersed to continuous phase, we had initially developed a solver in Fluent, wherein we basically coupled standard species transport equation with the within the POF framework. So as you can see, this is your basic scalar transport equation for C field. So this particular equation gets in the particular term S, which is source, which is nothing but the volumetric source term, which basically specifies the amount of solute that is being transferred from dispersed phase to continuous is absorbed in term S, and this gets invoked only in the integration cells. And this is basically the methodology by which you implement mass transfer in Fluent. So the downside of this solver was that you need to have an a priori knowledge of what amount of mass transfer was actually being transferred across the interface. So we began to search a model which was more robust, by which we could have avoided this, and we came across a paper by Holger, wherein they had actually proposed something called continuous species transport model. So this is your original species transport equation, and these are the boundary conditions, the flux continuity at the interface, and you can also expect some kind of concentration which is given by this expression, where m is the partition coefficient. So at the interface, from the concentration point of view, it has to respect these two boundary conditions. So what these people did was they actually absorbed these boundary conditions into this equation, and they had a modified species transport equation which is basically applicable in the entire domain. You would see that by doing this you get these two extra terms, which gets invoked only in the implication regions because of the terms gradient Ti and gradient alpha. So these terms go to zero in the pure phases, either the dispersed or continuous phase. So today I will just be showing how to couple this in the this kind of equation in the existing Interfoam framework. I'm going to be getting into the details of Interfoam, but I'll just take you through the steps that you have to go through. So coming to solver development, so basic steps that you have to do in modifying any of the existing solvers is that you create a copy of the actual application that you are targeting. In this case it's Interfoam, so you copy all the source codes and other files associated with it to your local directory, and you modify the solver, and once you compile it, the executables will be available in the user admin directory. So before we go into solver, this slide basically shows the overall relationship between your source code and the header files or classes that it is accessing. Suppose this is your application solver given by the name newapp.c. Here you can see that it accesses a class called nc.c, which has a header file containing definition of the member classes and the functions, and this is the main source code for that class. So once you compile this using a wmake command, it basically creates a binary executable named by .so extension. And whenever you try to compile your main source code, you don't have to recompile the already previously compiled class.c files. Rather than that, what it does is that during this runtime, it directly links searches for .so files and links to the executable created. So, if you look at the structure of how the application file folder looks like, this is the application folder which contains domain code with .c extension, plus it has other header files which it will be accessing. And plus, for compilation, you have OpenFOAM uses WMake feature for compilation, and it normally looks out for details in these two subdirectories and these two files in the make. So files basically contains list of all .c files which have to be compiled, and the executables are generally stored in user admin. You can always change it too. And options contain all the locations of the header files that the newer.c will be accessing, plus the libraries which will be linked which will be linked to the .c file. So, as I mentioned, so we will basically be coupling the modified transport equation with the interFOAM solver. And as we have seen earlier, in this case we have to the standard interFOAM solver doesn't have any definition for the diffusibilities and other parameters which can be associated with this equation. So we have to make provision in the existing solver which will allow it to access the values of diffusibilities of each of the phases. We have to create a volume scalar field for the concentration field, and also we have to add a parameter m which is nothing but partition coefficient. So there are many cstFoam.c is the modified interFOAM solver, and it accesses many header files and classes. But major classes that we have to worry about is something called immiscible incompressible two-phase mixture and the incompressible transport model class. So since Appear deals with a two-phase mixture, we need to define the properties for individual phases. So these details are contained in these libraries. So cstFoam.c would basically access the immiscible compressible two-phase mixture, which in turn points to new incompressible two-phase mixture. So we have to modify these two libraries before we modify the actual solver. And once we compile, we should be able to get a solver with a coupled UF and modified transport equations. So at this point, to basically execute these commands, to basically create a copy of the actual libraries. So if I show you, so I have basically created a folder called practice.x. So I'm not actually tinkering with the actual original files that are part of the original source code, and I have basically copied all the files which exist in the interFOAM. And so applications contain the actual solver, and as run folder basically contains all the case files that we are going to run, and SRC folder contains list of the transport models that we are going to modify. So if I expand this, you will see the incompressible model and the immiscible two-phase model. We basically rename it as a new immiscible two-phase so that there is no conflict with the original .c file stored in the OpenFOAM libraries. So the first step, as I said, is it's incompressible, is to modify new incompressible two-phase mixture.c. So I've already opened it here. So the main task here is to add the diffusibilities for the two phases. So in the .h file, new compressible two-phase .h file, the first task is to go with the declaration of these two variables, and then we have to come to construct part of this .h file. You have to you basically, since this is a dimension scalar quantity, you basically copy a template like existing template like one for OH2, and you try to add two more subsections, each for DC1 and DC2, which is basically diffusivity for phase 1 and 2 here, and you write and those are the only modifications that you have to do within file. So you have to, first thing is that you have to declare DC1 and DC2, and then you have to add it in constructor field .h. Now these are the only modifications that needs to be done to .h file. Coming to .c file, you have to notice first thing that you may have to modify is that initially for the original interface solver, this could be incompressible two-phase mixture .h. So now that you have modified and renamed the .h file, you have to make sure that you are accessing the newly modified .h file. So you rename this, and then you add the private members according to the definitions that has already been given in .h file. So everything remains same except for the DC field that you have to add. So again, you copy the existing template for a dimension scalar quantity, and you create copies each for DC1 and DC2, and then you create a volume scalar field for DC. DC is basically, it's a mixture. The way it's defined is basically a mixture diffusivity. So it's the product of alpha 1 DC1 plus alpha 2 and DC2. So that definition goes in here, and plus you will require, since you will be calculating divergence, you will require the phase values of each of these DCFs that you are creating. So you basically create a surface scalar field here. So these are the only modifications that needs to be done to your new incompressible two-phase folder. So once this has been done, before you compile, you have to make your changes to the .c to the contents of this file basically. So we basically renamed the file names, so you make the changes accordingly over and this particular line shows that kind of changes that you do. And the library, once it's executed, it would create .so file, and it gets saved in user.libnim. So what you do is that once you do this modifications, you go to options. There are no changes in the options file to be done. Once you do this, you execute the wlimit command and compile the modified solver. And what you should find is, so this is my user directory. If I go to lib, it would have, I have already compiled this, so it creates a .so file with the .c file name that we have just modified. So this is the .so file which gets generated. So now basically we are done with this part of the section. So we have compiled it, and we already have a .so file, associated .so file created in user libraries. So the next step, as I had shown in that flow diagram, is to modify the immiscible two-phase mixture library. This contains basically it accesses a header file called interface properties, which has details regarding the interfacial tension that will be provided through your case files, and it also calculates curvatures and evaluates the interfacial tension forces across the interface. So we don't have to do any modification to this header file, but we have to just do some modifications to the immiscible compressible two-phase mixture that was originally part of InterFOAM. So again, this. So this is your .h file. So the only modification that you have, it accesses the incompressible two-phase mixture. So you just change the header, name of the header files so that it points to the new .h file which was created earlier. And coming to the .c file, this is the only, again, you just ensure that it's pointing to the newly created .h file. And again, sticking to the same rule, before you compile, you have to make the appropriate changes. So this is the only .c file which you will be compiling at this stage, and again it will, once it's executed, the .so file will be created in the user.lib directory. And coming to options, so this particular .c file would be accessing the header files of new incompressible two-phase mixture, which is located in this directory. So you basically include that in your exe_inc portion of this file, and you also have to include the new libraries for the new incompressible transport model CSS. So this was the .so file which was created by compiling, when we compiled these files. So once this is done, you again you would compile this library, new invisible incompressible two-phase mixture, and once that's done, it would again create a .so file associated with these files. If you want to see that again, so this is the .so file that gets generated once you compile these files. Now that these two files or classes have been, the modified classes have already been executed, and this will be, the next step will be to modify the original InterFOAM solver. So before we do that, we actually create all the, create a copy of InterFOAM solver in the local directory by executing these commands. So this slide basically shows the components of the InterFOAM solver. So the only files that will be modified to get cstFoam is createField.h, because in cstFoam you will be solving for an extra scalar field represented by C. So you have to make those additions, and that will be done in createField.h. And to access these create fields, you will also have a dedicated equation to include the scalar transport equation for C in C equation.h, and cstFoam.c will basically access C equation.h. So I will just show how it's done. Next slide. So coming to the createField.h, you have to basically add three fields. So one is for the diffusibilities, one is for the partition coefficient, and you also have the density, mixture density in this case depends on the solute concentration. So you have to also supply an additional transport property in form of the solute density, and then you define a separate segment which would this particular segment basically basically creates a scalar, volume scalar field for the variable C, which is nothing but the concentration of the species and molecules. So if you want to have a look at that, I'm sorry. Where do you specify the dimensions for C? It's basically a dimensionless parameter, so it varies between 0 and 1. So that's how we have defined it. Okay. So yeah. So coming to create field of H.
You still have to declare it as a dimensionless parameter, putting everything as 0.
Yeah.
Because there is a place where you specify.
Right. Yeah. That's how to do that. No, like any scalar is dimensionless. Dimension scalar is like then you have to specify 0 things. If you just do it as
scalar, dimension it, you have to
specify. As we had done for diffusivity. Diffusivity we had it was not with diffusivity. I think it was with the M, I guess. The partition coefficient is again a dimension scalar.
Yeah, concentrations are dimensionless, partition coefficient will be dimensionless.
Right. Can you just show the place where you did diffusivity and partition? That's what, like in the same file, I think in the top.
Create field?
Yeah, in create. So this is the place. This is basically a dimension scalar. So these are the properties that you have to basically add to the existing Untitled solve. So it would already have provision to access rho 1 and rho 2, which is density of the individual phases, and you just make these additions. And another thing that you have to add is that you have to make a provision for creation of a separate scalar field for C variable. So coming to the next modification that we have to do, we have to now actually add the scalar transport equation, which was described earlier. So I hope to describe this will give you a fair idea. So this is basically the contents of C equation dot n. So this is the standard way by which the equation can be defined in OpenFOAM. So this term takes care of the transient part, and we basically create. Now when we do this, when we apply divergence theorem, this will basically you have to access the phase values of phi c and phi d. So phi c basically corresponds to this term, this entire term, and phi d corresponds to this term. So and the divergence over here basically defines the divergence term which will be calculated for divergence which will be calculated for these two terms. So you need to access the phase values, and that is being done by defining the surface area and phi c and phi d which will be calculated. So this value will provide surface values, phase values for each of these quantities, and which will allow us to calculate the divergence as depicted by this term and this term. So this is how you include your overall scalar transport equation. And the last step that you have to do is you have to ensure that this equation is actually accessed by the Untitled solve. So here what we are doing is it will be accessing various header files and basically Untitled uses an approach called MULES, which stands for multi-dimensional universal limiter explicit solution. I don't have much information on at least in this talk. Probably that's something I have to explore. And it uses MULES method to calculate the alpha equation. It basically reduces the diffusivity of alpha. With the artificial diffusion? Yeah, numerical diffusion. It takes care of it.
That's not the new something is for to maintain the possibility of alpha.
Yeah, it's also boundedness.
Is that additional term in that alpha equation is to
That's
compress the
basically.
interface into different things for different purposes.
But it has the flex limit of it.
The flux being there, yes.
Yeah,
I think Chenway is referring to.
Yeah. In the mutes, like, oh, okay.
That one is for, it's not for
The term that Chenway is referring to.
It's for mutes is only for bounded mix.
Okay, this one. It's basically this term. OpenFOAM basically uses compressive methods for resolving the interface. So that's basically absorbed in, by defining an extra term. So VR is basically known as compressive velocity, and it depends on a parameter called C alpha, which will be defined in every solution under case. So if you have its value as 0, so this term won't be taken into account and there won't be any compression. However, if it value of 1 for C alpha basically says it basically invokes compression, and if you further increase the parameter, the value of that parameter to 1.5, the interface becomes crisp. But it also, there was a paper which I actually went through it. It said that if you increase it to 0.5, there were some spurious currents which they actually observed at the interface. So it all depends. Most of the people say that the value of C alpha should be kept at 1.
So this is to have a sharp interface.
Yeah.
But then in mutes they have this lambda plus lambda minus, right? What is that? Yeah, the limit is the flux limit is lambda plus and lambda minus terms in the mutes are there.
What my understanding is the equation is only forming the bottom is somewhere.
Yeah, that's important, but the way it maintains is by making corrections to the flex term.
Okay, thanks for all this.
Actually, yeah, I haven't gone into detail of those. So once you have done all the modifications to the files, go to next job is to compile. So you will be compiling in the files. In the file called file C, basically mention the name of C file that you are going to compile, and you specify the location where the executables will be, once created, will be saved. And in the options, you will be accessing the two header files, the two libraries which cstFoam was accessing. One was immiscible incompressible two-phase mixture, the modified one, the modified library, and this will be in turn will be pointing to the other incompressible two-phase mixture library that I had modified. So once you do that, you again execute wmake command, and if you do that, you will have a executable created into a user library, user directory. Yeah, this is the solver that this is the executable created when you actually compile the solver. So now that solver is created, I will quickly show how to set up a case for this, a case file for this solver. So as you have already seen in the earlier presentations, so this is the overall structure of your case file. So it has a system directory which has provisions of supplying numerical schemes for discretizing each of the individual terms in the equations that you are solving. Every solution basically shows the methodology that you will be adopting to solve these equations. Decomposed part basically contains the methodology by which the partitioning of your domain is will be done for parallel execution. And control deck will have all the information such as your time steps, the start time, the end time. And in this case, if I take you to the case file which I have just filled, so you can see that control directory, it specifies the application that needs to be executed. So you have a start time, end time. You can also specify the intervals at which the files time directories have to be written, and you can specify the maximum prudent number, global prudent number. That will basically be important in some of the cases wherein it's been sort of expensive. Decompose part basically contains the methodology in which the partition will be done, and in this method I'm using Scotch.
How are those prudent number forced?
So basically, it's in this we are basically adopting something called variable time step. As you do it in Fluent, right? So it basically varies time step. So it checks for global prudent number. It accesses all these files access header file called prudent number.h or something. So it basically returns the maximum and total prudent numbers.
What do you specify adjustable?
It's here.
No, when you say adjust time step,
adjust time step.
so that's the starting time step, delta t.
So this is the starting time step that I have mentioned, and you can also, it's similar to what you do in Fluent basically. When you want to have a adaptable time step, when you want to go for adaptable time step, you can specify the maximum prudent number, and you can also specify the maximum time step that you can have.
Inside every runtime loop, there will be two header files. Read this thing. Kuva numbers.h and then the set delta t.h.
So you will keep on checking it every time.
You will read the Kuva number, the current delta t, and then it will give a new delta t. If you choose this option.
Right.
Is it effective? Like,
Yeah, it's quite. I think it's effective. What the problem is, if it's your problem is diverging, right?
suppose, that's what I'm saying. Suppose your solution is accelerating, velocity is increasing at certain point in space, and this solver decides based on the previous iteration, right? So it has 0.1 meter per second, and it will adjust the delta t according to that.
Yeah. And even the problem here is, even if in one cell, if it doesn't satisfy the CFI condition, then it reduces the delta t. And the delta t goes to 0.00041.
Right.
But I don't think so.
E power minus 6, e power minus.
It will go less than the delta t that you have already specified.
Yeah, you have minimum delta t, so that will, but it will lock onto the minimum delta t.
Is there minimum delta t? No.
I don't think so.
There is no.
No, there is no minimum delta t. There is only maximum delta t. This delta t value is the maximum. There is no point in setting adjustable time step, but if you are going to give a minimum delta t. But it would be nice if that option.
It would be nice if there was a limit on minimum delta t.
But it doesn't have.
Right, I think that's not a big issue, because once again it will increase the delta t. It's a Kuva number. Right? Once the fluctuation dies away, right? Once it gets closer to steady state, once again it will get the Kuva number and delta t, and it will increase the delta t. It should.
So can you define different current number for different equations? For example, this one is the flow current number, right?
This is for the alpha basis.
So that will be what, the cell size times velocity divided by delta t.
I think it's already cell size,
Something like that.
because
right?
it's the local Kuva number.
But how do you define it for something like concentration equation?
How do you define Kuva number for that?
Choose the
You just take the characteristic velocity.
Right. And luckily concentration thing propagates slower than the flow, so it's going to be okay.
But is there a definition like Kuva number like that for the?
Should be, right? This is. It has to do more with how the solution changes with space. It doesn't have to do much with physical velocity.
For now, this Kuva
There
number.
will be different current numbers, I suppose.
Yeah, for this, for number how it's calculated.
Based on the advection velocity.
Right.
It's a nonlinear advection.
Right.
So the advection velocity will be the same in all the transport equations.
So it's U
Because any quantity that is transported with the velocity.
Right.
So okay.
It's the same velocity, right? In that appears in the momentum equation as well as in the conjugate equation.
Here, for example, that is the concept, the interface. That adds one more different term because the interface changes and local diffusivity changes like that. So that is another phenomenon which is not just convection.
So in alpha equation, the convection velocity will be again accessing the
Right.
velocity from which is U.
Maybe probably that's why there is an alpha current number here.
Where's the alpha? So in IntoFoam you have this.
Yes.
I don't see this in IntoFoam or.
This should be there because the interface changes its location and then everything changes because the diffusivity is also included. The diffusivity is function of which phase it is in,
Do you
right?
know how this alpha one number?
It should be there in theory.
We can
Test probably, which might be. Yeah.
But is there some option like this in Fluent? Like when you do
No.
interface tracking?
No, there is only one current number it's used.
I'm also looking at this for the first time, alpha
Yeah.
one. Because in two-phase are different.
Even in two-phase you can specify it.
Yeah, I have to look into it. I've never
Probably this is the criteria which it will. This will be the student.
Can you just comment this thing and run the case once?
This one?
Yeah.
It will probably.
I just want to see if it's a default of, like you need to specify it.
Maximum.
Yeah.
Before that, coming to FP schemes, now that we are calculating two additional divergence terms, so you have to define discretization schemes for those two terms. That's being done in these two lines. And this is divergence phi C, or divergence of dot C in this equation. And coming to FP solution, so everything stays same except for the you have to include the methodology that we'll be using for solving the C equation. That's it. And I have another direct dictionary called set field dictionary. This will be used for initializing. So the case in which that I will be running, which basically it's a rectangular domain into which I will be patching a sphere and I will be releasing it. So that sphere would be defined by this. The center of this sphere is defined by these coordinates, and it will have a radius of around. It's basically a 4.5 mm droplet. This is the initialization. This is how you achieve initialization. So you have the alpha field equal to 1, which represents the disco space. Plus it will have initially it will have a concentration of 0.5. That's the scale back. So now that we have commented it out, let's see it. Next week's. Shows the error. Keyword is undefined. So I think it looks for that. Checks for that. Probably if we specify the adjust time, we had actually invoked that option, right?
Yeah, you can say
Let's see. Case one. System. So if I say specify this as no, we will not try this. Let's see. So this is the case file that we were running. So this is the sphere that we achieved by initialization procedure. So it has a C value of 0.5. That's the procedure. So at this stage, you put first 3 and reduce it also. You can see that these are the concentration fields as the concentration is at convected because of the motion as well as diffusion. So I'm using some arbitrary parameters because of high reduction for probability. The droplet attains some kind of sinusoidal shape.
How fine is your mesh?
What's that?
How fine is your mesh?
It's very good actually. You can display it in a bit of let me just. I'm not sure if I'm using the.
Yes.
No, why?
And don't use any color instead of alpha chlorobenzene.
Is this solid?
Yeah, solid. It is fairly.
It is fairly fine.
It is
I thought I was using the window file. This is basically a 2D there.
So this partition coefficient is like Henry's coefficient, right?
Yeah.
It's still valid for unsteady. Right?
It basically sets a limit on the amount of solid that will move out of the
It's like getting the C star from pressure,
Right, it's something like
but for liquid.
But this is for liquid equilibrium.
But only at the interface,
Only at the
Yeah,
interface.
which is an isovelocity.
Right.
But it is always an equilibrium. Fluent doesn't have this implementation.
No. The only way is that you have to specify the mass transfer. You have to define that volumetric
The
source.
source term, yeah.
But this partition coefficient, is the mass transfer calculated based on it, or does it act as a limiting condition?
Mass transfer would be calculated based on the gradient of flux
Okay, see.
either side of the surface. But at the interface there could be a jump in concentration. And so the concentrations on both sides of the interface are related by the equilibrium, which is your partition coefficient. And it's not.
Like, does it uses like a check condition, like, or is it calculated based on that?
It is estimated based on that. So see, there is chlorobenzene droplet, and continuous phase is water,
Right.
and the tracer is acetone.
Yeah. But sorry, the solute is
Solute is acetone. Let's say it is acetone. So there is acetone inside the droplet, and concentration is 0.5 in units. So the concentration just on the inside of the interface of chlorobenzene water droplet, just on the inside, will be some number, and just outside the interface will be some number. And that the ratio between these two is always constant. That's what we assume.
That is such only at steady state.
No, even unsteady state. That's what I was asking.
Even in unsteady state, the assumption is it's limited by solubility.
Right.
Right? And that's an equilibrium condition.
So that kinetics is assumed to be a lot faster. A lot faster than the rate of mass transfer. So if you imagine this, that the rate at which molecules are crossing the interface is much faster than the rate at which they are removed by diffusion and convection.
Okay,
Then this local equilibrium is always in place, and I hope there are methods to measure this thing carefully, right? There would be. Yes. How do you measure that?
We did some experiments in undergrad where we used to
Yeah,
have this
that's why I'm asking. Like, we elevate to equilibrium.
I mean, it depends upon what solute that you are at.
So,
Then
I get your point.
Huge interfacial area, and then let all the solute that going to be transferred, and then you have what is the concentration in either phase.
Right.
Could you use instead of chemical concentration, could you use chemical potential instead?
What's the theory behind this stuff? Visual. How to derive this, like from some dynamics, or why is there this?
You can get it.
Yeah, that's what Gauss was saying. The theory is that under equilibrium, the chemical potential is the same. So it's continuous.
Yeah.
Okay, but chemical potential is related to the concentration, and that concentration experiences a jump at the interface. So one could pose the problem of convection diffusion of the chemical potential instead of the concentration. In principle, it's possible, but I'm not
You can do that. But you have to know what the properties are in both the continuous phase and
Yeah.
so the data is what if you have the data you can propose them.
Yeah, I mean, there is a relationship between chemical potential and concentration.
Yes.
Right, so if you have the equation written in terms of concentration, in principle you can transfer it in terms of chemical potential is still a scalar form.
But it will be once again a function of concentration.
Well, they are related, so you can either express it as a concentration. There is a map that goes from concentration to potential.
And that is the Janaf tables and all that.
But it's a logarithmic expression, right? Mu equals RT log C, something like that. Right.
But still, it will be able to reflect this.
How valid is that sort of relation when you say R?
No, like for liquids there are separate tables.
That has to be different because R, when you say R, has to be thermodynamically, it should be gaseous state. Otherwise, you need some sort of correction, and then correction becomes empirical parameter.
No, that RT ln C is for gases.
Right.
For liquids there are
There has to be some correction.
there are different models.
Basically, when you involve
Activity
Yeah, activity
that will be empirical.
Yeah.
But basically, when you have this thermodynamic theory, the interaction between molecules is neglected or either isotropic, assumed isotropic. So if you have liquids, that's not the case. They will have more stronger interaction between molecules. So you will need to have this activity coefficients and stuff.
Right, in place of pressure.
It's beyond my expertise.
No, those models are available in OpenFOAM. That activity, its thermodynamic library is there. Combustion people, they do it. Like, yeah. So if you're interested, like, you can implement it.
don't see any implementation on this line. It's basically it comes to the basis.
So for this, at least Henry's constant is known. Partition coefficient.
Partition, yeah.
If you know the chemical species, right, everything you know, if they have these data tables in implemented libraries. So you can
Need to access them.
it's there, it's already there. Everything.
Someone at least to solve the to access those.
So as far as the interface is clearly resolved,
Yeah.
that is very sharp, this thing will work, right?
It should work. We are using the same model for microchapter.
So what happens if the interface becomes a little diffuse, if the adaptation is not working very well?
Basically, we will always do some kind of grid dependency test. So,
Right.
if you have data from experimental subjects, so suggest concentration.
Because however much you resolve, it's never going to be very sharp. There are always going to be at least one cell there. What's the sensitivity of flux to that kind of?
If it's very coarse, definitely you can expect a higher mass transfer rate than you not as you could have observed in experiments.
Right.
Because definitely the fluxes that we see.
We are using the species transport on the outside because you don't have. Yeah, it's just always there. Okay, that's it. We can close it. Okay, thank you.
Oh, one question. You have done something about the density. Is density connected to concentration?
Yeah.
So it also takes care of
It
its
takes care
acceleration.
because this C varies between 0 and 1, right? So
Right.
depending upon the concentration and this goes to different continuous space. So
Changes
it
density.
appears as the that's something that we included.
Okay.
That's why they dropped it actually as a
Right.
Earlier that was the problem. We didn't do that modification. So in the later version we basically had this dependency.
So where does that relate? Where is that from defined?
That's in the momentum equation. Rho G, but rho is a function of C.
Right, right.
Rho is a function of C.
There is a definition that continuous U. That's right.
Right.
So it's basically function of alpha. So it's basically product of the alpha, C and zeros.
Right.
So it's in pure phases. Suppose in continuous phase alpha 1 will be 0. So the density will be calculated in the last two terms. And that's the reason why you are actually reading an additional parameter in the transport properties. That is nothing but the density of your solution.
Right. Okay.
So this is basically incompressible. The base.